The last class we discussed log-antilog amplifiers. Let us now consider how a multiplier can be built using log-antilog operation. This I had illustrated in the end of the last class. Suppose we develop a voltage which is summation of log of voltages V t log, these are all diode voltages, V t log V x by I e naught R x, this is one log amplifier voltage, plus V t log V y by R y I e naught minus V t log V r by R r I e naught, then that voltage will be looking as V t log V x V y, this will be getting multiplied, divided by I e naught squared R x R y multiplied by I e naught. So, I e naught gets cancelled R r, okay, divided by V r. So, that is the voltage that you develop, and that voltage, if it becomes the forward biasing voltage of another diode, then you take an antilog of that voltage, that means that will be I e naught exponent V diode divided by V t. So, this V t gets cancelled, it is exponent log of this value, which is that value itself V x V y by V r, R x R y R r, I e naught getting cancelled. So, that I illustrated as a sort of place where it is not necessary to use compensated amplifiers, because when you take log and antilog, both effect of V t and I e naught get cancelled. So, this current is got. This is a very accurate method of getting this multiplier, and this current, when it is made to pass through a resistance, develops an voltage which is V x V y by V r. If I make R x, R y all equal resistors, then we know that this becomes V x V y by V r, and V r can be made equal to 10 volts, and we have the multiplier. But this is one quadrant multiplier, because you please note that all these diode voltages are valid for one polarity of the current. Okay. So, this is called a single quadrant multiplier, single quadrant multiplier, because V x, V y and V r can only take one polarity. Okay. In this case, let us say plus. How to implement this scheme using, let us say, op amps and transistors is what we are going to now see. This is the circuit of a log-antilog multiplier. Let us see what it is. I have the op amp here, and V x is connected and R x is connected like that. So, that current in this is V x divided by R x. So, this converts this voltage into current. This current is now made to flow through the collector of a transistor, which means that is done by the op amp negative feedback. Okay. So, this op amp has a negative feedback arrangement such that this current is forced to flow through this. If that current flows, then the voltage here is going to be V b e corresponding to that current, which corresponds to nothing but minus V t log V x by I e naught R x. So, this voltage here is nothing but minus V t log V x by I e naught R x. So, we get here this voltage straight away, but the thing is, I can, for negative feedback, keep this connected to this output. Now, I just want to digress a little bit and say why this is not connected here. This particular thing is not connected here because look at this log amplifier of ours. If this is like this is what we discussed as a log amplifier. If you consider this as a feedback circuit, the original amplifier was getting fed back from this point, unity gain feedback. Now, you are putting output of this to an amplifier here. This is nothing but a common base amplifier. This is fed to the emitter, and at the collector load you are taking the output. So, it is not a simple op amp, it is an op amp with active feedback. In that there is normally passive feedback is used. Here in this case it is a thing with active feedback, because feedback factor can be more than 1. So, this feedback factor in this case is nothing but Gm into R, where Gm is 1 over Re of this transistor. This is the gain of this, and there is no phase shift between this voltage and this voltage, which is common base. Therefore, this is a negative feedback with feedback factor itself equal to Gm into R. If the amplifier gain is A not A, then A into Gm into R should be less than 1 when the phase shift of A is equal to 180 degree. That is the condition for frequency compensation, otherwise it will go into oscillation. Normally what is done for making these op amps work is, when the phase shift of A is equal to 180 degrees, magnitude of A is made less than 1, but that will be violated here when the phase shift of A equal to 180 degree occurs at the same frequency as the other one, but the magnitude of the whole thing, loop gain, even if A is less than 1, is not going to be less than 1, because Gm into R may be greater than 1. So, this might go into oscillation even if the op amp is compensated for unity gain. So, this will go into oscillation. How to prevent this, or how to use compensated op amp here and not cause any oscillation in this circuit? That can be done by reducing the gain here. So, that means Gm has to be reduced. Gm is reduced by putting a resistance in series with Re, let us say Re1. So, this Gm, instead of small Re 1 over small Re, it will be 1 over small Re plus Re1. So, that R over Re1 is less than 1. So, that is the idea for putting a resistance in series here. Now, whether you put a resistance or not, the voltage developed is going to be always the same in order to make this current flow. So, this is something that you have to see, that in all log amplifiers they will put a resistance in series in order to make it work for the same frequency compensation arrangement as before. Now, what happens to the output voltage? Obviously, Re1 can be made very large, so that this gain can be reduced considerably. That is not the point. As Re1 is increased, the voltage which is necessary to for a certain current is going to increase, because suppose 1 milliampere flows through this. Normally, if you have not put a resistance here, the voltage would have been the diode voltage, but now that you have put a resistance, this voltage has to rise up to 1 milliampere into Re1. That should not go up to the supply voltage. That means, Re1 cannot be increased so much that it goes up to supply voltage. So, this is the limitation of this circuit. Now that we have understood the presence of Re, how to select it, we can further discuss about the circuit for multiplier. So, we have already developed a voltage which corresponds to minus Vt log Vx by Rx I E naught with respect to ground. Now, to this voltage we have to add minus Vt log Vy by Ry I E naught. So, that we can add by putting another diode whose current is supposed to be equal to Vy by Ry. So, that can come in series, addition of base emitter junction. The collector of this should be all the way connected to this point, so that the current is Vy by Ry. In order that the feedback is effective, obviously the emitter of this is connected through another Re2 to the output. So, you can see that this transistor base to emitter junction voltage is decided by the negative feedback arrangement of this. So, Vy by Ry is the current here, and this collector current is supposed to be the same as this. So, emitter base voltage is going to be that minus Vt log Vy by Ry I E naught, and that gets added automatically here if I connect the negative feedback. RE2 has the same property that I mentioned about RE1 in order to make the frequency compensation become valid, and also in order to prevent the op amp from going to saturation in that attempt. Now that we have got here a voltage which is summation of minus Vt log Vx Rx by Rx into IE naught minus Vt log Vy by Ry into IE naught here. This is what we got, of course only negative sign. So, this is a negative voltage. This is a negative voltage comprising of some of these. Then I had to subtract from this another voltage which is minus Vt log Vr by Rr IE naught. I had to subtract, or what I can do is I can arrange for these two voltages to be the difference voltages, okay, both are negative, okay, and apply that as the diode voltage. Okay. So, this also I generate with respect to ground. What is the voltage that we want to generate? Corresponding to minus Vt log Vr by Rr IE naught. You can see Vr by Rr is the current here, and this collector current is supposed to be the same as that. If the emitter resistance, let us say Re3 is properly chosen, so that it is connected to the op amp output, automatically this voltage is developed. So, this voltage minus this voltage is going to be the voltage that is going to be the voltage between these two terminals of another base emitter junction, which will convert the voltage into anti-log, okay, current. So, this voltage now is nothing but this negative voltage minus another negative voltage, and that is more negative on this side and more positive on this side. So, this is forward biased by a voltage which is equal to this exactly. So, this generates then a current which is I diode, which is going to pass through a resistance R, okay, and therefore, that will be developing a voltage like this. So, V naught is going to be nothing but ID into R, this is at 0 volts. So, this amplifier converts that current into a voltage ID into R, and as you can see here, this if you have 4 op amps and 2 pairs of transistors matched, you yourself can build a very accurate log-antilog multiplier. These matched pairs of transistors are available, okay, very readily as transistor arrays. You can build a multiplier very easily, and this will be very accurate, okay, as long as they are perfectly matched. What you have to remember is this is only a single quadrant multiplier, because the current can only flow in this direction in all these things. So, Vx, Vy, Vr have to be all positive in this case. So, it is going to work only in one quadrant. So, only in this quadrant it is going to work, but that is not a very serious limitation, because by properly selecting this operating point of this, I can make it work for signal which is going both positive and negative. That means, I can put Vx as equal to Vx dash plus 10 volts, Vy as Vy dash plus 10 volts. So, what I can do is Vx can be put as Vx dash plus 10 volts, Vy is Vy dash plus 10 volts. Both Vx dash and Vy dash have to go to plus minus 10 volts. That means, effectively Vx and Vy will have to go up to 20 volts in this case. Therefore, if Vx and Vy limits are made equal to 20 volts, 0 to 20 volts, then Vx dash and Vy dash can be made plus minus 10 volts. Okay. Then we will do the multiplication using this. This will be Vx Vy by Vr, which is Vx Vy by 10 volts. Vr can be made equal to this 10 volts. So, Vx Vy by Vr. So, what it will become is Vx dash plus 10 Vy dash plus 10 divided by 10. Okay. So, this is going to be equal to Vx dash Vy dash by 10, which is what we want here, plus now you will have error components in this Vx dash into 10 by 10, that means this will have Vx dash along with it, then Vy dash into 10 by 10, that is plus Vy dash, okay, plus 10 into 10 by 10, that is the offset. So, this has the x feed through, y feed through and the offset, which can be subtracted because we have already Vx dash and Vy dash as input to the multiplier. So, you subtract Vx dash, Vy dash and the DC offset 10 volts, then you will get at the output of this, okay, which is Vx dash Vy dash by 10 volts as the apparent multiplier. So, any single quadrant multiplier can be converted to 4 quadrant by means of the pre-bias arrangement. Okay. Once again, we made Vx is equal to Vx dash plus 10 volts. So, that Vx dash can vary from plus 10 to minus 10 volts as desired by us, when Vx is going on varying only from 0 to 20 volts, because it is single quadrant. Similarly, Vy, when it varies from 0 to 20 volts, this Vy dash can vary from plus 10 volts to minus 10 volts. Then we get the multiplied output of this multiplier, single quadrant multiplier, as Vx dash plus 10, Vy dash plus 10 divided by 10, which will give us the wanted output, which is Vx dash Vy dash by 10 plus Vx dash plus Vy dash plus 10 volts. This can be deducted, okay, from the total output of the multiplier by using another operational amplifier, which we know how to design, because in our earlier discussion we have discussed how to design an amplifier which will subtract whatever voltage you want to from the output. So, the offset can be removed, the x feed through can be removed and y feed through can be removed. So, that output of that op amp, which is subtracting all these things, will be giving you the 4 quadrant output Vx dash Vy dash by 10. So, this particular thing we will work out as an example, so that we can design a 4 quadrant multiplier out of a single quadrant one. Consider this example in order to illustrate how to convert any single quadrant multiplier into 4 quadrant. Example 25, convert the single quadrant log-antilog multiplier to 4 quadrant operation with minus 10 volts less than or equal to Vx Vy less than or equal to 10 volts dynamic range, Vr equal to 10 volts. So, let us assume that this is my block that we have already discussed, log-antilog multiplier with single quadrant operation. So, we want to give this, let us say, input Vx and Vy, output we will get as Vx Vy by 10 volts by making Vr equal to 10 volts. Only thing is how to select Vx and Vy such that, okay, it is operated in single quadrant, even though our actual input is plus minus 10 volts dynamic range. So, we have to assume that we will give this Vx dash and Vy dash. Okay. So, this is going to become Vx dash and Vy dash into 10 volts. Okay. So, basically we have to have now Vx dash and Vy dash as, okay, nothing but V x, this is V x dash and V y dash. V x plus 10 volts is V x dash, V y plus 10 volts is V y dash. Okay. So, this can be easily done with the help of an op amp. This op amp I do not have to really draw, because all of you are knowing how to do it. So, one simple way is so you have here, let us say V x, let us say, and this is 10 volts. Okay. This is R. So, what will appear at V x dash is minus V x minus 10 volts, minus V x minus 10 volts. So, if this is operating only in one quadrant corresponding to only negative voltages, right. If it is operating with only positive voltages, then what we have to do is apply minus x V x and minus 10 volts here, then this will be plus V x and plus 10 volts, or use a summing amplifier which will not give a phase inversion of 180 degree, that also can be done. I just want to illustrate the point. Now, another one where we will give minus 10 volts and V y minus V y. So, V y dash now becomes plus 10 volts plus V y. So, now output is V x dash V y dash by 10 volts, which is essentially speaking equal to V x plus 10 into V y plus 10 divided by 10, which as I told you earlier has the wanted component of V x V y by 10 and x feed through of V x and y feed through of V y and an DC offset of 10 volts, which has to be deducted from this. So, let us assume that this is going to be another amplifier that I am going to use for the purpose of subtraction and all that, how to do that. So, we have from this 10 volts to be subtracted. Okay. This particular thing, let us say, is going to be there such that is going to simply invert this. Okay. So, 10 volts to be subtracted from this has to be applied to, you have minus 10 volts, you can therefore add minus 10 volts to this, right. So, this minus 10 volts is already here. So, in this you have plus 10 volts, you are therefore subtracting minus 10 volts. So, if these are all R and R, that purpose is achieved already. So, the DC offset is already removed. Next, we have to remove V x. We already have minus V x here. So, that also can be added simply. So, it is a very simple circuit which is going to be giving us whatever we want, R at this node. Then similarly, we want to remove V y, can also therefore put this R. So, that is the circuit, very simple circuit. That will at the output now give, what will it give at the output? in fact it will give you minus Vx Vy by 10 volts. Okay. If you are not happy with the inversion, you can put another inverter and get rid of that, but that is not, because basically it is a 4 quadrant multiplier, whatever be the polarity of Vx and Vy. We have not really given now any polarity to Vx and Vy. So, it is just simply that if this is minus Vx and this is minus Vy, this will be minus Vx Vy by 10. Okay. If this is plus Vx and this is plus Vy, which could as we can as well call that, okay, then this will be still minus Vx Vy by 10, right. So, it does not make any difference. So, this is a 4 quadrant multiplier, okay, conversion using single quadrant multiplier as the basic building block. This is a commonly adopted technique, and the dynamic range remains the same, okay, as what we want, plus minus 10 volts. So, this is a precision multiplier which can be used up to hundreds of kilohertz. Primarily the frequency limitation is due to this op amps which are not readily available for very high frequencies, right. So, up to hundreds of kilohertz, if you want to design a very good precision multiplier, this is the technique. This is very cheap. Let us now discuss another important popular multiplier. This is available also in IC form. This is called transconductance type multiplier, or actually the basic idea emanates from what is called Gilberts Cancel. Discuss what this Gilberts Cancel is. This uses a very important principle called Translinear Principle in bipolar transistors. What is that translinear principle? The Gilbert Cancel is given here. This is a very important cell. This comprises junctions, base emitter junctions or diode junctions, okay, forward biased, but forming a loop. So, this translinear principle is applicable to any loop formed by forward biased diodes. It could be just simply this, just I have so many diodes, let us say, with some kind of currents coming in here, okay, and maybe current coming here also. So, suppose we have a string of diodes, all of them form a loop, let us say. Then the Kirchhoff's voltage law is valid here, that the total voltage in this is 0. Summation of all the voltages in this should be equal to 0. What is required in this translinear principle is number of diodes connected in the clockwise manner. Let us say these are all clockwise forward biased, these are anti-clockwise forward biased. These numbers should be the same. If that is the case, then the product of the currents in each of these diodes, let us say this is I1, okay, up to I1, and this will be, let us say, I01 up to I0n. The product of the current of these anti-clockwise connected diodes, okay, is the same as the product of the currents in this. This can be easily proven because summation of sigma of all these voltages should be equal to 0. That means, the forward biased diodes in clockwise direction should have the voltage equal to the reverse forward biased diodes in the anti-clockwise direction. Therefore, we have let us say n number of diodes. So, I is equal to 1 to n, okay, VBE I, okay, should be equal to, let us say, VBI of these, we will call this A, okay, for clarity, and this as B. So, that those are which are A, okay, should be same as VBE B I is equal to 1 to n. This is from Kirchhoff's law. So, once these sigmas are same, we know that this is same as V t log, these V b's are same as V t log corresponding currents, which we are calling I 1 I A, okay, by I E naught, okay. And this is also equal to sigma V t log I, let us call it J B, okay, J is equal to 1 to n, right. So, these V t's get cancelled, okay, V t log I J B by I E naught. These V t's get cancelled. Logarithm of sum of these products, sum of these is equal to product itself. Product, okay. I is equal to 1 to n is same as log. So, that means product of j equal to 1 to n. This will give you 1 over I E naught to the power n. This also will give you 1 over I E naught to the power n. So, this is the basic principle, translinear principle, very important. What it simply says is, right, if there is any loop, closed loop formed of n number of diodes in clockwise direction, n number of diodes forward biased in the anti-clockwise direction, then the currents flowing through the clockwise direction diodes, product of these, will be equal to current flowing through the product of the diodes which are in the anti-clockwise direction. Let us apply it simply to, for example, a current mirror. A current mirror is the first example. For example, one diode with another junction. So, this current in this should be same as this current, that is single diode. So, that is the basic principle of translinear, this thing applied to a pair like this. Now, here this is slightly more complicated. You have two diodes and two junction transistors connected in a loop. So, according to this, now these are, let us say, diodes which have one polarity and these are diodes which have another polarity. The current through these diodes, product of these, should be same as the current through these junctions. That means, actually speaking, you can now see that I D 1 is the current through this. So, I D 1 into current through this is essentially I C 1, okay, because it is I E 1 which is very close to I C 1. This is equal to I D 2 into I C 2. This is what the Gilbert Cancel says. Product of the current of the diode, okay, into this transistor, corresponding transistor, is equal to product of the current of this diode into this transistor, or I D 1 by I D 2, I D 1 by I D 2 is equal to, okay, I C 2 by I C 1. This is valid over a wide range of variation of current, because this is not a small signal thing. We have assumed large signal property for the transistor, exponential relationship, and that relationship is valid for almost 6 decades of variation of current, and therefore, this is a very powerful signal processing aspect, okay, which has been used in many applications of integrated circuits. But now, we would like to use this for multiplier. You can see here already current multiplication is taking place. I D 1 by I D 2 into I C 1 is equal to I C 2, or we can see here that I D 1 minus I D 2 divided by I D 1 plus I D 2 equals I C 2 minus I C 1 by I C 2 plus I C 1. I can make this two currents equal a constant current, that is the Gilbert Cancel, a constant current I naught, force the current to be constant. So, that means I C 2 plus I C 1 is equal to I naught. So, I D 1 minus I D 2, the differential input current divided by I D 1 plus I D 2, the common mode input current, twice that, into I naught, which is a DC current, is equal to I C 2 minus I C 1. Okay. This is the basic principle of Gilbert Cancel, I naught into I D 1 minus I D 2 divided by I D 1 plus I D 2 equals my differential output current I C 2 minus I C 1. If I select currents I D 1 and I D 2 such that it has a common mode current which is a DC current and a differential mode current which is the signal current, how do I do it? I can make I D 1 okay, equal to, let us say, I naught naught, okay, a DC current by 2 plus, let us say, I let us say delta I by 2 input current, differential current, and I D 2 equals I naught naught by 2. This is the common current which is common to both, minus delta I by 2. You can see here I D 1 plus I D 2 okay, will have this getting cancelled. So, it will be simply I naught naught DC current. Okay. I D 1 minus I D 2 will have this getting cancelled okay, and it will be simply delta I. Okay. This is how we had represented common mode current, common mode voltage and differential mode voltage in difference amplifiers. Okay. Same way any two currents can be represented as a common current and differential current, okay, a common current and a differential current. Okay. So, this one I D 1 is equal to I naught naught by 2 plus delta I by 2, I D 2 is equal to I naught. Then what happens to this? This becomes I naught, I D 1 minus I D 2 is delta I, that is the differential input current. I D 1 plus I D 2 is simply I naught naught. This is of great significance because you can see I naught naught is a DC current I said. Suppose this is 1 milliamperes and I naught is 10 milliamperes. You are getting a gain of 10 for the current amplifier okay, as the output differential current. This is the input differential current. Okay. Output differential current is simply 10 times input differential current. This is unique in this because such constant gain we could only obtain in other schemes by giving negative feedback. This is having no negative feedback. Okay. This is independent of temperature, active device, anything. This is dependent purely on current ratios. How can I get current ratio like that? I use current mirrors. Okay. Let us say 1 milliampere current mirror, I use 10 times in shunt, I get 10 milliamperes. Okay. So, it will be an absolute constant okay, independent of temperature and all that. So, we can get okay, current gain without any effort, and these are all what are called wide band current amplifier circuits. That is why this Gilbert Cancel is very famous today as a basic building blocks for current amplifiers. Okay. Here the voltage never changes above VB, all these voltages are V diode voltages, and therefore, the capacitors need not be charged to large voltages. That means, time taken for operation of this circuit is very small. That means, these are all high speed circuits. Okay. So, these circuits are nowadays being used as okay, wide band amplifiers with constant gain, and you can reach the required gain by simply cascading such structure, because this differential input could be the input to the next stage, which looks exactly identical. Only thing is the operating current of that is, let us say, 10 times more than this. Okay. So, you can put one structure over this other structure, that is why it is called a cell. Okay. So, the next stage will be having two other diodes connected to same VCC with this as input now. This has now, as you see, a differential input, okay, and a common mode input. Common mode input is nothing but I naught. Okay. So, this can become the input to the next stage, and that will be exactly looking like this with this current operating at a higher value. Okay. That much should be sufficient for Gilbert's gain cell. Now, how to use this for multiplier is something that we have to discuss. This circuit, as is shown here, is the circuit which is able to convert a voltage into differential input current required for the Gilbert's gain cell. After all, most of the signals that are available to us are going to be voltages. So, even though this Gilbert's gain cell tells us that the output differential current is input differential current into I naught by I naught naught, there is some kind of multiplication taking place in terms of currents, but we would like this to happen in terms of voltage. So, we need a voltage to current converter, but that voltage to current converter should be voltage to differential current converter, which is required as input to this gain cell ID1 and ID2. How to do that? This is called a trans conductor block. This does it beautifully. You can look at it. Vx is the input. Okay. We have here a current which is going to be, let us say, I naught naught by 2, I naught 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 by 2. That is the common mode current, okay, constant current, and this is linking the two emitters. You have a resistance Rx. So, what happens now? This current is I naught naught by 2, and this current is going to be Vx. Okay. Vx will come across this Re1, Rx, Re2. If you neglect this Re1 and Re2, this Vx will directly come across Rx. You can select Rx such that it is large compared to Re1 and Re2. Then the current in this is Vx divided by Rx. So, the total current here is I naught naught by 2 plus Vx by Rx, and the current in this is I naught naught by 2 minus Vx by Rx. So, simply we get a linear transconductor here which converts a voltage into what we want, a constant current with signal current equal to Vx by Rx added to it, another constant current with signal current Vx minus Rx deducted from it. That is exactly what we want as the input to the cell here, ID1 and ID2. So, that this be ID1 and this be ID2, okay, inputs to this. Okay. Then what happens? We will now know that output, which is IC2 minus IC1, equals I naught, okay, divided by the I naught divided by I naught naught, okay, because it is ID1 plus ID2 into delta II, which is nothing but Vx twice Vx by Rx. Okay. This is delta I by 2, this is minus delta I by 2. Okay. So, delta II is twice Vx by Rx. So, we are able to now get Vx here. The differential output current is directly dependent upon Vx now, and we want it to be multiplied by another voltage. What can we do? Obviously, there is only one choice. I naught has to be dependent upon another voltage. let us say that I naught is really equal to I naught by 2 plus V y by some R y, just as we had here a voltage to current converter. We can have voltage current converter there also, only thing is it will be V y here and R y there. So, that can generate a current which is in one side I naught by 2 plus V y by R y. So, this current can be generated. Instead of therefore a current source of I naught, I will simply put I naught plus V y by R y there, a current source. How do I get that? That can be got by putting here the same thing R y I will put, and then I naught by 2 I naught by 2. So, here I get, if I put V y here, I naught by 2 plus V y by R y. So, you have this being connected here and this current source. So, you have a multiplier component here in this differential output current, you have this. What to do with that? That can be applied to another one which is also connected to same pair, similar pair like this. This same input can be given to another pair like this. So, this is going to be taken here, and that means this is also going to have similar ratios for the current, because same input is being given. So, we will call this T1, T2, T3, T4. The current in T3 and T4 will be, let us say IC3 and IC4. So, these ratios will be exactly similar to what we had as ID1 by ID2. So, we will have this equal to, let us say IC2 minus IC1 here, IC2 minus IC1 is similar to IC3 minus IC4, IC3 minus IC4 divided by I naught naught Rx twice Vx. Only thing is here it will be I naught by 2 minus V y by R y, right, because this current source current is different. So, you can see here that this whole arrangement we have the product that is got, but only trouble is that there is some feed through component of Vx here. So, is the output here. So, that can be simply got rid of by subtracting this from this. So, this differential current can be subtracted, that means IC2 minus IC1 minus IC3 plus IC4, therefore, becomes equal to these two will get cancelled, we will get twice Vx by Rx I naught naught into what is this, twice Vy by Ry. So, you will get here 4 Vx Vy Rx Ry I naught naught, which is the product of two voltages, that as the current. This can be converted into a voltage by multiplying this whole thing by a resistance R. Right. So, how do I do that? IC2 plus IC4, IC2 plus IC4 simply can be done by connecting those two together. This is IC2 plus IC4 node. Then IC1 plus IC3, that is going to be these two currents. So, this current is going to be IC1 plus IC3 and make these flow through resistances R. and connect it to VCC and take differential output voltage V naught. Okay? That is going to be nothing but this. So, this is called a 4-quadrant multiplier, because Vx and Vy both could be positive or negative. So, this is the complete transconductance multiplier, which is available as an IC. We will discuss the application of this and variations of this circuit in the next class.